So now here's an approach that does work. It's the semi-implicit approach. Semi-implicit approach is actually you split up the Coriolis term into half from the current time level and half from the next time level. And this is shown here in these equations. Let's activate the mouse. Here we go. You can see 0.5, and then you split up the component of the v velocity component into time level n and time level n plus. And the same here for the u. The alpha is just a reformulation of this one. Is just delta t time step times f. Okay, and then you can rearrange these terms. And again, why do you need to rearrange them? Because that's in a numerical model. You have always the unknowns, the unknown on one side of the equation, everything known on the other side of the equation, and you do that, and then you get a rearrangement, and these are your predictors. You know that this is your iteration that you. And if you do that with this scheme, you get a perfect solution. Okay? However, you get a little bit of bias of the period, how long it takes. So your path is on a circle and it's perfect also, but the time scale can be biased. So this is the semi-implicit approach for Coriolis force, and it turns out to be relatively tricky if you have more than the Coriolis. If you have other terms in your model, then the formulation is quite tricky of this semi-implicit approach. Not trivial. Bottom friction is trivial. You can always do that. Okay, but with the Coriolis force, it is a relatively complex. Okay, so let's have a look at another approach.